with apologies to fifth period, sorry, I want to revisit this problem number 6. We talked about and have a recording, a different recording, when I discussed the tensions at the top and bottom of the vertical circle. And what we did was we erased all this stuff in here, the timing units, and I said that there was an issue with that because of the fact that I gave values here of 1/2 mg and 3/2 mg and all that stuff for this the tension function as a function of time, or the tension in the string as a function of time as it was swinging in a vertical circle. So the apologies to fifth period come from the fact that I said that I couldn't solve it with the time in there because I gave values, but I did not give numerical values. I gave them in terms of m. So let's go back and let's re-establish the time frame here. Notice that each of these tick marks is 1/10 of a second. So we can solve this. I can show several different ways that the tension in the string is consistent with what we would expect the tension to be for a radius of a given amount. Okay, so in other words, we can find the radius based on this information that's provided in this graph. Roundabout way of saying all that. All right, so what's really easy is we know that the tension when it's on the side, this is the easiest way to approach this problem. Let's say it's swinging this way. The tension when it's on the side, mg is perpendicular to the radius. So there's no component of mg that helps the string provide that centripetal force towards the center of the circle. All right. So the centripetal force here, if it's equal to a value of mg as indicated on this graph, then it's pretty easy to just run down here and say that mv squared over r, or because we are given period of revolution here of 0.8 seconds, we could say 4 pi squared r over t squared is equal to that's the centripetal force requirement. And where does it come from? It just comes from the tension when we're on the side. Okay? If it just comes from the tension when we're on the side, then based on the tension that we're given being equal to mg, it's real easy to see that m's cancel out, and we get 4 pi squared r over t squared is equal to g, and then just rearranging that, we're going to get that r is equal to gt squared over 4 pi squared, and so the radius of this circle equal to g 9.8 meters per second squared times 0.8 seconds squared times, or divided by, 4 pi squared. And dimensionally, we would come up with seconds squared would cancel out, and we would just get meters, and that's what we would expect for a radius. All right, so the value for this, when we crunch out all these numbers, radius was equal to, I ended up getting 0.16 meters, 1.588. So 15.8 centimeters, 16 centimeters, however you want to look at it, depending on your sig fig deal there. So 0.16 meters. Now, I can show also that this is consistent with the fact that we have a maximum and a minimum of what do we end up with? 3/2 mg as a maximum and 1/2 mg as a minimum. All right, so here's the maximum at 3/2 mg when it's at the bottom and 1/2 mg when it's at the top. You can see that the average force is just going to be mg, so that helps us figure out that this expression right here is valid. This one right here. And but another way of doing that is to just you can see that if we say force of tension at the top, right, is max, and that's equal to, we know from doing a free body diagram before, at the top is when it's at a minimum. Sorry about that. So force minimum force, which is equal to, we have mg acting downward, we have tension acting downward. Here's mg and tension. We know that the net force is equal to 4 pi squared r over t squared, and we get that net force is equal to both tension and gravity are acting towards the center of the circle, so we're going to say force of tension plus mg. So when we put these together, we get that the force of tension is going to be equal to 4 pi squared r over t squared. That's our centripetal force requirement, minus mg. That's the algebra of that. That's why it's at a minimum. All right, analogously, if we were to go through and do the same thing, this is, this is min. All right, and if we do tension force max, if you go through exactly the same process, you'll find out that it's 4 pi squared r over t squared plus mg. All right, so Ft max, Ft min. All right, we know that both of those are equal to Ft max, so what I did was take those two equations and set them to the known values that we had, which were respectively for the minimum 1/2 mg and 3/2 mg for the maximum. All right, so I'm just going to take those two equations. Now watch, this is just a little bit of algebra stuff. All right, I'll just have to write them all out again. All right, so we know that 4 pi squared r over t squared minus mg was equal to, this is our minimum, right? And the minimum value we had was 1/2 mg right here. So that's equal to 1/2 mg. And then for the maximum force, we had 4 pi squared r over t squared plus mg is equal to, go back and look, that's 3/2 mg. And so just a little bit of algebra here. I'm just going to add these two equations to each other. All right? If this is equal to this and this is equal to this, then this plus this, going down this way, are equal to this plus this. All right? So what we're going to get here is 8 pi squared r over t squared. Negative mg plus mg is 0, and that's going to be equal to 2 mg, the sum of 1/2 and 3/2. All right, so it's pretty easy to see that we could just take here, divide through by 2, and we end up with 4 pi squared r over t squared is equal to mg, which is exactly what we had before when we just set it equal to what was going on when it was on the side, if you recall that green drawing that I had before. Okay? We just said Fc is equal to mg, not because this is mg, but because the graph says it is. Okay? So since we ended up at exactly the same point, just go back there and you do exactly the same math, and we end up with the string length equal to 16 centimeters, just like we did before. Here's that same expression I said before. Actually, it's got the m's in it. Nope, I left the m out. Whoa! Should have been an m in here the whole way. M times that, and m times that. Sorry about that, but the m's could have canceled all the way across. Doesn't matter. Yep, I left it out over here too. Sloppy. All right, so the m's cancel all the way across. You can cancel them out at any point. So here the m is here, because I hadn't canceled it out yet. And we'll go ahead and cancel it out at this point. And we'll just see that g is equal to 4 pi squared r over t squared, not mg. Okay? So that's the same place we were when we calculated and found out that it was equal to 0.16. Here we have 4 pi squared r over t squared is equal to g. 4 pi squared r over t squared is equal to g. All right.